Okay, in this video we discuss a special kind of router tree called binary tree and two basic properties of binary trees. So let me start by giving the definition of a binary tree. So a binary tree, it is a tree in which there is exactly one vertex of degree 2 and all other vertices are of degree 1 or 3. Okay, so it is a tree in which there is exactly one vertex of degree 2 and each of the remaining vertices is of degree 1 or 3. So this is how we define a binary tree. So a binary tree is defined to be a tree in which there is exactly one vertex of degree 2 and each of the remaining vertices is of degree 1 or 3. Okay, so let me give one or two examples of a binary tree and a tree which is not a binary tree. Okay, so let's consider this tree. Okay, so here if we look into this tree, we can see that the degree of this vertex is 2, the degree of this is 1, degree of this is 1, this vertex is 1, degree of this vertex is 1, and the degree of this vertex is 3, and this is 3. Okay, so here we can see that this tree satisfies this definition. There is exactly one vertex of degree 2. Okay, and each of the remaining vertices is of degree either 1 or 3. Okay, so this is a binary tree. Okay, so let me give an example of what is not a binary tree. Okay, let's consider the same tree that I drew here. Okay, suppose that I add one more vertex on this edge here. So now we can see that if you look into the degree of each vertex here, okay, degree of this is 2, 1, 1, 1, 1, and degree of this vertex is 2, degree of this vertex is 3, and this vertex is 3. Okay, so here we can see that it doesn't satisfy in this definition. Okay, so there is here we can see that we have these two vertices having degree 2. So here the definition says a binary tree is a tree in which there is exactly one vertex. So here we have two vertices of degree 2. Okay, so that says this is not a binary tree. Okay, so a binary tree is defined to be a tree in which there is exactly one vertex of degree 2 and each of the remaining vertices is of degree 1 or 3. Okay, and if you look into these examples, you can see some important properties. Obviously, okay, we can see that a binary tree has 3 or more vertices. Okay, so let me write down what I said. Okay, so we can surely see that any binary tree has 3 or more vertices. Okay, for example, if you consider a tree with a single vertex, we can see that here we have only a single vertex and the degree is 0. So that violates the condition for this definition. Okay, so definitely it is not a tree. It is not a binary tree. Okay, and suppose that we have a tree with 2 vertices, and since the tree is connected, it will look something like this. Okay, so again we can see that these two are not binary trees. Okay, here if you look into this one, we can see that the degree of this vertex is 1, degree of this vertex is 1. Okay, but the definition says there is exactly one vertex of degree 2 and each of the remaining vertices is of degree 3. Okay, so here if you look into this tree, we do not have a vertex with degree 2, so that is not a binary tree, and that says okay, any binary tree has 3 or more vertices. Okay, and again we can see that here if you look in the definition, that says there is exactly one vertex of degree 2. Okay, so that particular vertex is a unique one. Okay, so we can always designate that vertex as the root, and that says a binary tree is a rooted tree. Okay, so let me write down what I said. Okay, so here we can see that since the degree to vertex okay, it is distinct from all other vertices okay, that particular vertex it serves as the root of the binary tree. Okay, and that says every binary tree is a rooted tree. Okay, so that's another important thing. Okay, since the degree 2 vertex is distinct. Okay, so here exactly one vertex of degree 2 from all other vertices, it serves as the root. Okay, and so every binary tree is a rooted tree. Okay, so that says, so if you look into this tree, so this vertex has degree 2 and there is only one vertex satisfying that condition. Okay, so that says okay, we can designate this as a root. Okay, and so we can consider this tree as a binary tree. So okay, these directions are implied here. Okay, so that's what the binary tree is. Okay, so let's look into two basic properties of binary tree. Okay, so let's look into two basic properties of binary tree. So first property says every binary tree has odd number of vertices. Okay, so before proving this, let's go through one or two examples. Okay, so here we can see that okay, this is a binary tree. So because here we have this vertex having degree 2 and that is going to be the root, and all other vertices have either degree 1 or degree 3. Okay, so it's a binary tree, and if you count the number of vertices here, 1 2 3 4 5 6 7 8 9. Okay, so the number of vertices is equal to 9. Okay, and similarly okay, we can see that if we add okay, one more vertex and edge here, okay, now we can see that the degree of this vertex is 2, so it is not a binary tree. And if you count the number of vertices will be 9 plus 1 10. Okay, so this statement says every binary tree has odd number of vertices. Okay, so let's look into one more example. Okay, so here again this is a binary tree, and here you have exactly one vertex of degree 2 and all other vertices have either degree 3 or degree 1. Okay, so if you count the number of vertices 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so again we can see that number of vertices is 9. Okay, so this is odd, this is odd. Okay, and this is true for any binary tree. Okay, every binary tree has an odd number of vertices. Okay, so let's go and prove the theorem. Okay, so it's going to be a very simple proof. Okay, so in any binary tree, okay, there is a vertex, there is exactly one vertex of degree 2 and all other vertices have degree 1 or 3. Okay, so this particular vertex, that root vertex, it has degree 2 and all other vertices have degree 1 or 3. Okay, here 1 or 3 are odd numbers. Okay, so by handshaking lemma, okay, by handshaking okay, we know that the number of odd degree vertices is even in any simple graph. Okay, so a tree is a simple graph anyway, it's a connected acyclic graph. Okay, so by handshaking lemma, the number of odd degree vertices is even, okay, in any simple graph. Okay, so that says the number of vertices that have degree 1 or 3 must be even. Okay, so if we collect all those vertices, okay, that is going to be even plus this vertex 1. Okay, vertex having degree 2. Okay, so even plus 1 is odd, and that says and that proves the statement every binary tree has odd number of vertices. Okay, so let me write down what I said. Okay, so therefore when the root, okay, so root has even degree, which is of even degree, is added to this number. Okay, this number means the number of odd degree vertices. Okay, number of odd degree vertices is even, right? So this number is even. Okay, even plus 1. Therefore, when the root is added to this number, the total number of vertices is odd. Okay, this 1 plus even number of odd degree vertices. Okay, so even plus 1 is odd. Okay, and hence okay, every binary tree every binary tree has an odd number of vertices. Okay, so that's the proof. Okay, so that says every binary tree has an odd number of vertices. Okay, and here the proof is somewhat similar. Okay, and look into the definition and just use the handshaking level. That's it. Okay, so let's go and prove one more property and a corollary that follows from this statement. Okay, so this statement says there are n plus 1 divided by 2 pendant vertices in any binary tree with n vertices. Okay, remember pendant vertices are vertices with degree 1. Okay, so they are also called leaf vertices. Okay, so this statement says there are n plus 1 pendant vertices in a binary tree with n vertices. Okay, so let's look into one or two examples. Okay, so let's consider this tree, and this tree is a binary tree. Okay, only exactly one vertex of degree 2 and all other vertices have either degree 1 or degree 3. Okay, so here the number of pendant vertices are 1, 2, 3. Okay, so 3. Okay, we can see that the number of vertices in the graph is 1, 2, 3, 4, 5. Okay, so n plus 1 will always be even. Okay, because of the previous statement, every binary tree has odd number of vertices, so n plus 1 will always be even. So in this case 1, 2, 3, 4, 5, n plus 1, 6. Okay, 6 divided by 2, which is equal to 3. Okay, so for this tree it work. Okay, it's a binary tree. Okay, so let's consider a tree that is not a binary tree, and let's see what is going to happen. Okay, so it looks something like this, and let me add one more vertex here. Okay, so here we can see that the number of pendant vertex 1, 2, 3. Okay, and total number of it is 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. Okay, 6 plus 1 is 7. Okay, 7 divided by 2 is like 3.5. Okay, so this is not equal to this one, so it violates that condition. And again we can see that this tree is not a binary tree because here we have two vertices of degree 2. Okay, so let's go and prove this statement. So that this statement says there are n plus 1 divided by 2 pendant vertices in any binary tree with n vertices. Okay, okay, so let T be a tree with n vertices. Okay, and let L be the number of pendant vertices. Okay, so if the number of pendant vertices is L, okay, then there are n minus L internal vertices. Okay, therefore there are n minus L internal vertices. Okay, for example, if you look into this graph, this tree, okay, we can see that the number of pendant vertices is 3, 1, 2, 3, and the number of internal vertices okay is 1, 2, 3, 4, 5. 5 minus 3, which is equal to 2. Okay, so these are the two internal vertices. Okay, so therefore there are n minus L internal vertices. Okay, and we know that for a pendant vertex the degree is 2. Okay, and when you consider this internal vertices, okay, one is the root vertex that has degree 2 and all other vertices have degree 3. Okay, so therefore okay, among this n minus L internal vertices, the root has degree 2 and the remaining n minus L minus 1 vertices has degree 3. Okay, so now what we are going to do is we are going to invoke the handshaking lemma. Okay, so by handshaking lemma, okay, 2 times the number of edges, okay, in that tree is equal to the sum of the degree of each vertex, right? So we have L vertices of degree 1 and we have a root vertex of degree 2 and the remaining, that is n minus L minus 1. Okay, so these vertices have degree 3. Okay, so 2 times the number of edges is equal to L plus 2 plus n minus L minus 1 times 3. And since we are dealing with a tree, so in any tree with n vertices, the number of edges is equal to n minus 1. Okay, so substituting that here we get 2 times n minus 1 is equal to L plus 2 plus 3n minus L minus 3. Okay, so that says 2n minus 2 is equal to okay, so L minus 3L. Okay, so these two cancels out. We get something like 2 plus okay, I think this cancels, so we get minus 1. Okay, and we get 2L here. Okay, so we will get 3n minus 2L. Okay, minus 1. Okay, and I think these will cancel and we get 1n here and okay, so minus 1. Okay, so we get minus 1 equal to n minus 2L, and rearranging this particular thing we get 2L equal to n plus 1, and that implies L equal to n plus 1 divided by 2. Okay, and that's what we are trying to prove. Okay, and that says the number of pendant vertices in any binary tree with n vertices is n plus 1 divided by 2. Okay, and that's the proof. Okay, so let's look into a corollary for this statement. Okay, so that says the number of internal vertices in a binary tree is 1 less than the number of pendant vertices. Okay, so let's look into this example. So if you look into this example, we can see that the number of pendant vertex is 3 and the number of internal vertex is 1 less than 2 here, right? Because similarly we can see that if you look into, okay, I think we have another binary tree here. Okay, this is also a binary tree, and here the number of pendant vertices are 1 2 3 4 5. Okay, so 5 minus 1 is 4. Okay, so we can see that number of internal vertices 1 2 3 for satisfy this condition. Okay, so let's go and prove this one. Okay, this statement, it follows from the previous one. Okay, so from the previous theorem we know that the number of pendant vertices. Okay, so number of pendant vertices. Okay, so let n be the number of vertices, and L and I be the number of pendant and internal vertices. Okay, so now we know that this n is equal to L plus I. Okay, where L is the number of pendant vertices and I is the number of internal vertices. Okay, and from the previous theorem we know that, okay, this L is equal to n plus 1 divided by 2, and that implies okay, and that implies n is equal to 2L. Okay, 2L minus 1. Okay, so substituting this in 1. Okay, substituting two in 1. Okay, we get 2L minus 1 equal to L plus I, where I is the number of internal vertices. Okay, so here this will cancel, and that implies I, okay, which is the number of internal vertices. Okay, it is equal to the number of pendant vertices minus 1. Okay, and that's it. That's the proof. Okay, and that says the number of internal vertices in any binary tree is 1 less than the number of pendant vertices. Okay. Okay, so that's all for in this video, and the next video, okay, we will see a generalization for this binary tree called MRA tree, and we will discuss some more properties of those MRA trees. Okay.